Hello good people, I'm supposed to calculate the delta G and the equilibrium constant for the following reaction. So I have two unknowns, delta G and K. I'm supposed to do some sort of calculation, yet I have not been given a single numerical value. Whenever I get stumped, I go back to stoichiometry and moles. Now that I look at this reaction a little bit closely, I can see that it is not balanced. I have two oxygens on the left and only one on the right. Also, I have two hydrogens on the right and none on the left. So I'll need to balance it somehow. The next thing I realize is that this is most likely a redox reaction because I have a metal reacting with oxygen. That means that this metal is most likely going to get oxidized. And I can check that by using the oxidation numbers. The oxidation number of silver is 0. The oxidation number of oxygen gas is 0. The oxidation number of an ion is whatever the charge of the ion is, so in this case, +1. The oxidation number of hydrogen is mostly +1, which means the oxygen has to be -2. And now I can see that the oxidation number of silver has increased, so silver got oxidized, and the oxidation number of oxygen has decreased. So oxygen got reduced. Okay, next thing I recall is that whenever I'm dealing with redox reactions, I should split the reaction into half equations. I will do silver first because that one seems a little bit easier. So I will have silver solid goes to, oops, that's not what I want to do, goes to silver ion, no, there we go, much better. And the other half is oxygen gas, goes to whatever is left, and that is water. Now I need to balance these half reactions. So up here I have one silver and one silver. That's balanced. There are no other atoms, no other molecules to worry about. So all I am left with is the charge. On the left I am neutral, on the right I am 1 positive. That means I need to add an electron here to make the right hand side negative. Sorry, not negative, but neutral as well. Okay. The second half reaction, I have two oxygens on the left, one on the right. Multiplying the water by 2 will fix that, but then I have ended up with 4 hydrogens on the right, which means I need to add 4 hydrogens on the left. And because they carry a positive charge, now the charges are out of whack. On the left I am 4 positive, on the right I am neutral. An easy way to make the left neutral is to add some electrons. So I need to add 4 electrons. Now I know that I need to add these two half reactions together, but to do that, the number of electrons has to be the same. Down here I have 4, up here I have 1. The easiest way to fix that is to multiply this whole half reaction by 4. That means I will have 4 silver solids go to 4 aqueous silver. That is not the symbol for silver, Ag, there we go. Aqueous, positive, plus 4 electrons. Now I am ready to add these two together. The electrons will cancel. That means I'll be left with 4 hydrogens plus oxygen plus 4 silver solids gives 2 waters and 4 silver ions. Great. Unfortunately, I still do not have a single numerical value. But then I remember that half reactions usually come up sorry, not come up, but come with standard reduction potentials, and I can look those up. So the standard reduction potential for silver is plus 0.8 volts. The standard reduction potential for oxygen is plus 1.23 volts. And I can use these two values to figure out the standard potential of the cell. The formula for the standard potential of the cell is E naught cathode minus E naught anode. That means I need to figure out which one is which. Well, up here I said that silver got oxidized and oxygen got reduced. And I can use red cat and an ox, which means that the reduction side is the cathode side and the oxidation side is the anode side. So now we can say plus 1.23 volts minus plus 0.8 volts gives me positive 0.43 volts. Fantastic! I finally have a numerical value. How can I use it? Well, there is a formula that relates E naught to delta G. And luckily, it's a relatively straightforward formula. It says delta G equals negative N multiplied by F multiplied by E naught. So what are those values? Well, E naught I have plus 0.43 volts. N is the number of electrons involved in the reaction, and up here I figured out that that is 4. F is the Faraday's constant, 96,485 joules per mole volt. That means I can use those values here. So I will have negative 4, I'll just put it in brackets, multiplied by the Faraday's constant, 96,485. Do not forget the units. Multiplied by E naught, which is 0.43 volts. And that equals, well, I can cancel some units. So this volt and this volt will go, which means I'll be left with joules per mole. And that's fantastic. That's what I want my delta G to be in. So let's see. Negative 4 times 96,485 times 0.43 is negative, let's make that white, negative 165,954 joules. Or I could round it up to negative 166 kilojoules. Okay, so I found one of my unknowns. I found delta G. Next thing, I need to find K. So is there a reaction, a formula that relates E naught to K or delta G to K? Well, there are both. So we can relate delta G to K. So delta G equals, pardon me, negative RT ln K, so we can use that formula, or we can relate E naught to K, and we can say E naught equals, pardon me, throat is getting a little bit dry from all this talking, equals RT over NF ln K. So it is up to you to decide which one you want to use. I'm going to use this one because it looks simpler. So what is R? Well, R is a constant, 8.314 joules per mole Kelvin. Temperature, well, at the start we said it's at standard conditions, which means standard temperature 25 degrees Celsius or 298 Kelvin. So I can use those numbers here. So I'll have minus 8.314 joules per mole Kelvin multiplied by the temperature, 298 Kelvin, multiplied by the natural logarithm of K. And now I can use those numbers, and I can also cancel some units. So this K and this K will cancel, and I will have 8.314 times 298, and I get minus 2,478 joules per mole. And I have just remembered that I should also add my delta G. And when I look up here, I realize that I forgot that this is per mole. So let me just add that unit. So delta G is negative 166 kilojoules per mole, or negative 165,954 joules per mole. I'll use that value here. Negative 165,954 joules per mole. Let me rewrite that. I apologize, I was a little bit slack. Ugh, that looks ugly. Let's fix that. Joules per mole. And this side still needs to be multiplied by ln K. Okay, sorry about that little misstep there. Okay, so now I need to get ln K alone on one side, which means I need to divide this value by this value. 165,954 divided by 2,478. And with rounding, I get 67. The joules per mole will cancel, so I have a unitless number, 67 ln K. K equals e to the power of 67. And if I use that in my trusty calculator, I get 1.25 times 10 to the 29th. So now we have found the second unknown. To recap, when faced with a complicated problem, always go back to little things that you know how to do, and that is usually stoichiometry and number of moles. If anything, it will buy you time for your other brain cells to kick in and hopefully guide you to the solution. That is all for now, and I will see you on the flip side.